This video presents the research project Varsity, a computer vision project for automatic semantic and dynamic city modeling. Varsity started in 2012 after Professor Kenneth Vanhoey obtained a 5-year funding from the European Research Council in order to conduct fundamental and long-term visionary research at ETH Zurich in Switzerland. Its vision back in 2012 was that many images of a city environment would become available in the near future through social media, availability of public webcams, and capturing vehicles like cars or drones. This data should be sufficient to not only model the city's geometry in 3D, but also capture its variation over time. Hence, Varsity was born and set out to advance automated computer vision techniques to be ready for processing this data and getting the most out of it. In over 5 years of work, Varsity involved 14 PhD candidates and postdoctoral researchers and produced more than 70 high-quality research publications. 5 companies collaborated on the project and 4 new ones were born in the process. As a result, Varsity produced a breakthrough in automatic applicability, completeness, and efficiency of city-scale image-based data processing. This video shows a comprehensible summary of the main achievements and example applications, including bringing large-scale 3D city reconstruction to a fully automatic level, producing a profound semantic understanding of the city's content, capturing and modeling the city's liveliness, and creating automatic video summaries of events and places. To start modeling the full city, we exploit highly overlapping images collected by an aircraft over the area of interest. By analyzing these images, we compute the precise 3-dimensional position from where each image was taken. This procedure also generates the 3D location of characteristic points that can be identified across multiple images. The point cloud is then updated to a more detailed version calculated from the images using modern multi-view stereo techniques. This data is then converted into a 3D surface model. Our novel algorithm preserves geometric details while producing a very compact mesh that allows for real-time visualization. The result of this procedure is a compact, textured urban surface model that is suitable for large-scale 3D rendering, navigational purposes, or 3D urban design. Additionally, we apply state-of-the-art machine learning techniques to partition the surface into meaningful regions like buildings, roads, vegetation, and water. This allows to understand the city composition, count buildings, or build a road map instantly. By analyzing the shapes of the buildings, we can estimate their architectural uniqueness and identify the most interesting buildings based on this criterion. This can be used, for example, for automatically creating an optimal tourist path for architecture enthusiasts. A closer look at the surface model reconstructed from airborne images reveals the lack of details on facades and street objects. This is due to the distant viewpoints the images were taken from. In order to capture street-level details, we employ industrial mobile mapping technology. Here we show samples of 5 out of 16 videos that are recorded from a car. The system operates in real time with 360-degree coverage of the environment. Streets can be mapped at normal driving speeds with this technology. The network highlighted on this map was driven in a single workday. In order to extract the 3D geometry of the scene from these videos, we track key points across all images. These key points are reconstructed on the fly as a sparse point cloud of the surroundings. The 3D points are updated in real time as new video frames become available. Next, we further process the street-side images and extract a dense 3D point cloud using multi-view stereo techniques. Some areas cannot be mapped using this technology. At this spot, for example, the car is not allowed to drive into a pedestrian-only square on the left. To also model this area, we exploit images taken by tourists and shared through social media, for example. As a result, we end up with corresponding camera poses and a dense 3D point cloud of the pedestrian-only areas as well. Here, the complete point cloud is converted into a street-side surface mesh by using conventional methods. This mesh already shows the relevant facade details that were missing before, like windows being set back or balconies sticking out of the main wall. However, the ground, higher floors and roofs are missing. In Varsity, we introduced an efficient method to fuse aerial and street-side data into a hybrid surface model. This model combines reconstructed ground and roofs with detailed geometry on the building facades. Here, the input aerial and street-side images are both used to texture the surface. In summary, we automatically produce hybrid surface models at different levels of detail over large urban areas. This enables many applications in emergency planning, urban design, preserving cultural heritage, or computer games. A key aspect of Varsity is to understand the city, which requires to infer knowledge from the acquired data. To do so, we automatically segment each image and identify people, cars, motorbikes, buildings, and other categories. The segmentations can be used to protect privacy, as shown here, by pixelization of sensitive areas. Since semantic segmentation on individual images can generate unstable results, we process the data all together. Thanks to the dense data collection, we have millions of images to analyze. For efficiency, we developed methods that select the optimal viewpoints. This is essential, as we only need to process around 15% of the data, making our solution scalable to the whole city. The segmentations produced on these images are then projected onto the 3D model and fused. As a result, our semantic segmentation solution produces a unique, coherent 3D segmentation of the full city. Facade details are detected automatically with 71% accuracy where high-resolution data exists. The more data is available, the more we can recognize. Our accurate understanding adds knowledge to the raw 3D geometry, which can be queried for automatic answering of questions like, how much surface needs to be painted on this wall? What is the height of the windows in this building? Or how bright are the rooms in this building? This augmented 3D model can also be used to build applications like voice-guided navigation systems. For example,
please move towards the facade with the green wall and red windows. You have found your destination.
Finally, we go even one step further in exploiting this knowledge so as to produce simplified geometry for each building. The resulting model encodes the facade into a few bytes, producing a very compact 3D model that matches the underlying structure and allows manipulation of the geometry. All these contributions augment the 3D model with understanding that can be used for many applications. For example, architectural planning, zoning law analysis within urban areas, or simply visualization. The next goal in Varsity is to measure variation and bring life into the virtual city. Let's start by modeling traffic. Here again, we exploit the large amount of drive-through data that we collected. For each camera stream, we automatically detect vehicles and pedestrians, and our algorithm generates tracklets from these detections. As we have these measurements for a single point in time, but for many places, we can propagate them to produce an initial estimate of traffic density in Zurich City. To improve this estimation with time variation, we recorded publicly available camera feeds. In this example, we exploit the footage of 13 different cameras from which we analyze traffic and identify parked cars at any time. In our project, we detect and count the vehicles and store this number with corresponding timestamps and locations. This data is exploited by our spin-off company Parquery, which provides real-time parking monitoring solutions based on camera footage. Using detection counts, we extend our initial estimate and simulate the traffic flow over time. From these simulations, we can observe how the traffic changes over the course of a typical day or a typical week. This can benefit transportation planning for both the city administration and road customers. Now that we have a model of typical traffic, we can also detect deviations from expected behavior. For example, our technology can immediately alert users when a road is closed or when an event is happening. Here we show such behavior where a typical social event is taking place in the city center. This technology can be taken to any level of detail provided data is available. We can, for example, automatically analyze detailed movement of vehicles and people in a particular area. Here we detect car trajectories over time and store car density statistics for each one of them. Similarly, we model the density of people walking around this square. Finally, because we're concerned with privacy issues, we replace actual footage by avatars following average statistical behavior resulting from our detections. We can then simulate the recorded behavior using our statistics. For example, at 4 o'clock when it's calm, or at 6 p.m., which we identified as the peak time. As a result, our contributions offer a respectful and realistic simulation of the typical city buzz at any time in the day. Finally, Varsity is also about processing user videos and images from social media for providing useful and fun applications. We processed thousands of publicly available images and registered them to our 3D model of Zurich. Similarly, we register each individual video by deducing a smooth frame-by-frame camera pose. This again helps us to understand where people walk and what they look at. All this media is automatically analyzed to identify the most interesting and informative video parts. As a result, we produce a coherent cinematographically edited summary of landmarks and events. Here again, our contributions can help in many applications, like creating automatic summary videos of outdoor events or places using hundreds of available videos. This concludes the demonstration of our 4 main topics of research. We have shown several possible new applications for the structured and semantic data we create, like visualization, automatic measurements of the city composition, traffic analysis, and creation of tourist guides. Many more are imaginable, like urban planning, catastrophe and disaster response planning, real estate valuation, geovisualization, games, and so on and so on. Recall that Varsity was based on the vision that many images of a city environment would become available in the near future. The data allowed us to produce what has been shown in this video. We used aerial data collected in 2008 to get a coarse overview of the entire city. Then, we collected street-side data in 2013 to map accessible streets with higher quality. And finally, we filled in the empty spots, like pedestrian-only and tourist areas over the time span of the whole project, using images from public webcams, aerial drones, or social media. This gives an idea of how much more data will be available in the future. Our projection is that in a few years, the entire city of Zurich can be covered with high-quality data. Such an amount of data can only be handled by automatic algorithms. And the Varsity research has now provided tools for the detailed and frequent modeling of cities.